electrical currents flowing through magnetic fields. And the idea here is that we've got a pattern that emerges. If you have a current flowing in the direction that the thumb of your right hand is pointing in, and the magnetic field is pointing in the direction that your fingers are oriented in, then the force that's felt by that conductor in the magnetic field is going to be equal to F equals ILB sine theta. Now, the fact that it's a vector times another vector and a sine theta, immediately, if you're a calculus and vectors person, you recognize that as a cross product. Has anybody done cross products? One person, two people. Okay, so and it depends on the semester that we're doing physics in. Second semester, obviously, like more people know what a cross product is. But there's two different ways to multiply vectors: dot products and cross products. Anytime you see two multiplied vectors and a sine theta, cross product. Anytime there's two multiplied vectors and a cos theta, dot product. A cross product produces a vector as its result. A dot product produces a scalar. And so kinetic energy, where you have velocity times velocity, that v squared thing, that produces a scalar. This vector times a vector, the third vector is perpendicular to the previous two. So we're getting pushed along as a product of the two other vectors. So I'll leave that for the math teachers to expand on further, but it doesn't have to be like charges that are confined to a wire that are moving through this field. It could be charged particles, just free flowing, protons or electrons getting fired through a magnetic field. And so I want to, with part B, let me see if I have a thicker marker here. With part B, I want to again bring up this idea of a north-south bar magnet that's going to produce a magnetic field orienting from north to south in the gap between those two field sources. And I'm just using bar magnets for convenience. Of course, these could be electromagnets or something like that. If they were electromagnets, we could fine-tune the intensity of the magnetic field between the two sources. I'm just trying to keep it simple. We're making these like just bricks of magnet. But again, keeping it simple, let's fire a proton. I know that electrons are typically the mobile charge, but let's just say that this is a proton being fired, like basic particle accelerator style, okay? Not a cathode ray tube. We've got this positive charge that's being shot through this magnetic field. So a couple of bullet points here. Positive charges flying through magnetic fields obey the third right-hand rule. RHR, right-hand rule. And a lot of people will call this third right-hand rule the motor principle. And the reason they call it the motor principle is because it applies a motive force, like that pushes something, right? Like in the case of the straight wire, maybe pushes it in the direction of the palm. But in the direction of this, in the situation of this flying positive charge, we'll talk about it getting pushed in a direction. Now, negative charges. So if this had been an electron flying through the air, so negative charges flying through a magnetic field, follow the opposite force rule. And what I mean by that is if a positive charge is going to follow the same right-hand rule that we just talked about before, because conventional current is this false idea of positive charges being in motion through a wire. When we say that it follows the opposite force rule, I've heard people say, well, how about we use a left-hand rule then for electric charges, because that's the opposite, right? But then I've heard other people say, well, why whip out my left hand if I've already got my right hand handy? And so that's what I'm going to say. Let's say, think this way. We're going to use a backhand rule. least that's what I do, because I always think I want to use my right hand for everything. So if it was a negative charge, I would say that this negative charge would get pushed in the direction of my backhand, right? So I'll model that out. Let me zoom out. If I've got a negative charge going in the direction of my pen through that magnetic field, I'd take my fingers in the direction of the magnetic field, and I'd say that the electron is traveling in the direction of my thumb. I would use the back of my hand as the backward slap on an electron that would slap it backhanded. If it was a positive charge, like in the current illustration, again, magnetic field in the direction of my fingers, positive charge in the direction of motion of my thumb, I would use my palm pushing down into the page. You guys follow the difference on that one? It's just, opposite charge, so opposite force pattern. Okay, that's all I'm saying. So let me zoom back in on this. Oh, sir. So think backhand rule, or if you're really committed to this, you can use a left-hand rule, okay? Because there's going to be some people out there that would like to use a left-hand rule, in which case you'd use your left hand. This is my left hand. I've got the magnetic field in the direction of my fingers, the flow of a negative charge in the direction of my thumb, and the palm would push it out of the page. It's the exact same pattern as the backhand rule, okay? So either or, it doesn't really matter to me. You just have to keep it straight for yourself. Remember, these handed rules are just patterns. They're patterns that help us remember what happens. It's not like they're fundamental laws of science or something like that, okay? They're based on rules, but they're just memory aids. Anyway, so the equation that we end up getting for this one, it reminds me a little bit of the previous one, in that there's a force, but it's QVB times the sine theta. Now again, it's sine theta, so we recognize that it's a cross product, but at the same time, there's no length of wire. What we have in fact here is a charge that's flying through space, so charge in motion, and of course we measure our charges in units of coulombs, and the V is the velocity of the charge. Of course, that's just given in meters per second. Now, I'm not going to go back and define what V and what theta are again, because we already defined those earlier when we wrote this equation the first time, but for straight conductors. So that hasn't changed. I'm not going to redefine those guys. I want to sort of do a little block out for my page. And just think quickly about doing an example. So in my example, again, I want to have this idea of having a magnetic source, magnetic field source. So I'll just draw a partial of a north pole there, give myself a south pole over here. We'll have a charge that's in motion, pew, 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 getting shot through that magnetic field gap. And remember, magnetic fields always orient from north to south. So we've got that field orientation there. I'm going to suggest that this Q, I'll draw a dotted line along its path. This charge, Q, label it, flies along a path like that, such that the angle between that path and the magnetic field is theta. Okay, so we got a charge that's flying through, and we can call this an overhead view. You can probably tell that it's hard to describe a scenario like this in words. So to get a block paragraph description of this often isn't the case. Often the people will give you, yeah, sure, the sentence description, but they'll give you the diagram as well, because otherwise it's a little bit hard to interpret a language-based only description of this. So let's just say that we've got this description. I'm not going to write out a paragraph for it. And I want to let Q equal negative 1.60 times 10 to the power of negative 19 coulombs. And so I'm going to jump right to it. I'm going to get into the dirty business of not using a positive charge, but using a negative charge right away. So we're going to have to deal with that backhanded rule right off the bat. We're going to say that it's flying through space at a pretty good clip, 8.00 times 10 to the power of 4 meters per second. Now, in previous lessons, we've talked about how we would get a particle up to a speed like that using an acceleration plate, like a charge acceleration plate. You guys remember that? The vertical plates versus the horizontal plates, the whole cathode ray tube thing. So we could get this thing up to speed using information from a previous topic. And we could say that we've got a magnetic field within this gap of equal to 0.300 Tesla. And previously, we've talked about what the base unit way of expressing Tesla would be. I'll just say it quickly in brackets here. It's kilogram coulombs per second. But typically, people will just write it as Tesla. But just so that you know what's hiding underneath of the hood of a Tesla, I guess that sounds like something that's like a car reference. But anyway, theta is equal to 50.0 degrees. Charles Auguste de Coulomb is hiding under the hood of every Tesla. There you go. And the mass of an electron, I looked it up, 9.11 times 10 to the power of, and it's a tiny one, negative 31 kilograms. Okay? So boy, that's like maybe an intimidating list of values, things that you don't necessarily have to have memorized. But here's the question, finally. Find the force acting on the flying electron. Of course, this is just plug and play. There's no real rearranging or problem solving here. We just want to make sure that we can do the data entry on this one. So F equals QVB sine theta. And even as I say that equation, I just find it like rolls off the tip of my tongue so quickly. And the reason is I probably spent like 2 or 3 years in university doing electromag charged particle problems. And QVB sine theta is just one of those things. It's like delta D equals V1T plus 1/2 AT squared. It just like, boom, it's like in your brain after you do 500 of them, you know? So negative 1.60 times 10 to the power of negative 19 coulombs. Eight times 10 to the power of 4 meters per second. 0.3 Tesla. And if you want to write out the full unit expression, you could, just to show that all the units cancel out, but I don't think I want to. Times sine of 50 degrees, the relative angle between the velocity and the magnetic field orientation. And when I plug all that in, I get somewhere around negative 2.94 times 10 to the power of negative 15 newtons. Now that's already pre-rounded to 3 sig figs. Did anybody already get that? Make sure that, okay, I didn't make a typo. Now the thing is that negative sign, what does it mean? Well, in this case, the fact that there's a negative sign, notice that we were never going to get a negative from speed. We were never going to get a negative from Tesla. We were never going to get a negative from sine theta unless we have a casserole issue. But go with the acute angle and you won't have a casserole issue. You know what I mean? So the only way that the negative sign is going to come up is if we end up having a negative charge. And so in this situation, if I was writing code for this, the negative sign would indicate backhand rule, right? Or left-hand rule, however you want to think about this thing. And so I'm going to have to translate that sign code into human language, 2.94 times 10 to the power of negative 15 newtons. And in this case, based on, oh gosh, I don't have a solid reference frame. How am I going to even indicate direction? If you're not given a nice directional reference frame, just make some sort of reasonable assumption, like north, south, east, west. I'd make north positive and east. Oh my gosh, not north, south, south. No two souths. I'd make north and east positive just for argument's sake. Not that it really makes much of a difference here. But the thing is, I need a third direction. So it's reasonable in this case that north, south, east, west doesn't actually help us right now. The only place it would help us would be like this is 50 degrees relative to the east, right? Or relative to the west, I guess. The reasonable direction that I would throw in at this point would be out of the page. And out of the page is a reasonable direction. Now, if you'd already defined this reference frame, instead of out of the page, can you say that we could say up? And so in these kinds of problems, if you have a north, south, east, west reference frame, sometimes people will give the direction up. Other times, like in all honesty, people will write in textbooks, they'll say out of the page. That's a reasonable direction, okay? So that's what I'm going to write now. Write it out of page. What do you think the opposite of out of page is? Yeah, into the page. And if you're stuck with the north, south, east, west planar reference frame, then it would be up or it would be down. Okay? Up. Well, so let me get my right hand ready. So my right hand, I'll zoom out. Remember, my right hand tells me that the magnetic field is going in this direction. My thumb is the direction that the object is flying in. But because it's a negative charge, I'm going to use the backhanded rule. It's getting pushed out of the page. Had it been a positive charge, it would be getting pushed down into the page. Okay, so this is like a, or if you're committed to using your left hand as an opposite, again, magnetic field in the direction of the fingers. Now it's a left hand because it's an electron in motion, so the opposite. And then I would say my palm is pushing it out of the page. Now, what you're going to encounter is, I bet you, some of you have moms, dads, aunts, uncles that have like a European or, I don't know, like a sub-Saharan African training. And they'll end up whipping out their right hand like this. Can you guys see that my middle finger, pointer finger, and thumb define an X, Y, Z axis? And it turns out that we can do something like this. We can say, okay, well, if my thumb is the magnetic field orientation and my finger is the direction of particle travel, then the electron is going to get pushed in the direction of my middle finger. That's fine. I'm going to teach the palm hand rule. But if you encounter mom or dad, and mom learned how to be an engineer in Korea, and she's using right hand rules that are like X, Y, Z finger thumb axes, fantastic. That's great. Just recognize it's only a memory aid, okay? So don't tell your mom that she's wrong or something like that. For goodness sake, it's just a memory aid. We all got to be okay with that. Everybody cool? Out of curiosity, has anybody seen this kind of axes? Like you've talked with an older family member or something? Yeah, totally cool, okay? I'm well aware of that. Partly I'm trying to match the textbook. Partly I think like my grade 11 physics teacher explained it that way with the palm thing. And so probably, we all have our own history, right? All right, so we could do a therefore statement, but I want to do another question. What would the acceleration of the electron be? We're always talking about particle accelerators with these things. If there's a force, then there must be an acceleration, because we haven't forgotten about Newton's second law. Remember, F net, how could we ever forget, is equal to mass times the acceleration of a system. And so for this one here, we still have A cis is equal to F net over m. We've said previously that the force due to gravity acting on an electron is so negligible, right? And so if we want to figure out the acceleration of this thing, we've already got 2.94. Notice I'm going to drop the negative sign because I already know what direction it's going to get accelerated. It's going to get accelerated out of the page. I've already landed on that. 2.94 times 10 to the power of negative 15 newtons divided by the mass of an electron, 9.11 times 10 to the power of negative 31 kilograms. I mean, these numbers are tiny, but that's okay. It's a tiny little thing. And don't be afraid if the acceleration ends up being a big value. That's not a terrible thing either. Anybody get an acceleration? Yeah?
3.2272 times 10 to the 15.
2272 times 10 to the power of 15? All right. Now you could say newtons per kilogram, but those of us who are in the know say meters per second squared. Yeah. Because it's acceleration, All right. But then in terms of the direction, we say out of the page. And people say, wow, that's a heck of an acceleration. I've never seen something accelerate like that. And it's going fast too, right? Like it's going at 80,000 meters per second. Dang, that's fast. Well, what's this thing going to do? I want to show you an illustration of what it does. It turns out, now zoom out. This is a teacher resource manual. Maybe I'll do it like this. So that the text, physics 12. This is a nice illustration of what it does. It turns out that if I had a radioactive decay source where my pinky finger is right now, shooting straight out the bottom of the letter I, you guys imagine this? Imagine that some of the particles getting shot out of that particle source are positive and some of them are negative. Are you with me so far? Let's pretend for a minute that the magnetic field that these particles are being shot through is oriented away from the camera, so into the page. Everybody follow? I'm going to take my right hand. I'm going to stick my right hand into the view of the camera. Get this right. So my thumb is pointing in the direction of those particles flying. Magnetic field is in the direction of my fingers going into the page. Notice that my palm is pointing to the right on the screen, right? That means that everything that gets pushed to the right is what? Positive or negative? Positive. Everything that gets pushed to the left is negative, yeah? That makes sense, right? Now, the fact that these things are accelerating as they get pushed to the right, they're positive, and you notice depending on their speed, they're going to keep on experiencing a force. Like when it gets to this point here, you notice that it's traveling, here's my pencil, it's traveling tangentially this way, but the magnetic field is still going into the page, right? So the force is going to be on it this way. So then when it gets to here, again, the magnetic field is still going into the page, so it's going to get force this way. Can you guys see that this is acting as kind of a centripetal force on these charged particles? And these charged particles, as they fly out, they're going to dissipate energy, because actually what we're seeing here is charged particles being fired into a space where we're getting glowing trails like this, right? So it makes sense that it's probably like a gas that's fluorescing or phosphorescing in some way. It's somehow, as the charged particles fly through this gas, the gas is getting excited and emitting photons so that we can see the trail. So these particles are losing energy, but as they do so, they're experiencing this magnetic force, and they're therefore experiencing a centripetal force that causes them to curl out to the sides. And so we could like look at this radiation source and say, okay, so out of this radiation source, some particles are positive, some particles are negative, and I can get a relative read on what the acceleration is that they're experiencing. And based on that acceleration that we're experiencing, we could talk about the abundance of positive charges, the abundance of negative charges. We could talk about how positive they must be, how negative they must be. We could talk about how fast they're going. Look, some of these things are shooting out almost straight before they start to curl. Maybe that means that they have a low charge, or it means that they're going really freaking fast. And that's something we need to investigate. That's kind of cool, right? Like we have these vapor trails, these glowing vapor trails in the presence of a magnetic field for charged particles flying through it. And that, for some reason, got put onto the cover of this teacher's resource manual. Now, this isn't even the textbook that we use anymore. I've only held on to this resource manual because I think this is a pretty picture, and it explains this idea nicely. Like, this is the closest thing I'm going to get to a demo because I don't own this equipment. But somebody did, and they took a picture and they slapped it on the cover of a physics textbook thingamajig because it looked pretty, right? But now we kind of have like some reason for knowing it, or at least some understanding of what it means. Let me try that again. I'm going to get my ooh la la. I don't even have a decent virtual demonstrator for that one yet. I always got my eyes open. So if you see one that's a glowing trail particles in a magnetic field demonstrator, let me know about it because I would love to play around with it. But I don't happen to have a virtual for that one.